James Arnold. I have experiment 3 for group 2. This experiment will be talking about the vapor compression, refrigeration cycle, and heat pump. So let's get right into it. So lab objectives for this experiment are to analyze the performance of a heat pump, which will be the evaporator in this experiment, and then we want to measure the coefficient of performance. Do this by determining the inlet power and produced heat, and then coming out with our COP, which I'll get into that a little bit later. And then we want to be able to describe this vapor compression refrigeration cycle using a pH diagram, which will be your pressure and enthalpy, and compare that real cycle that we have to an ideal cycle. So here's a lot of different ways you can describe a refrigeration cycle. I won't get into all of them, but the best labeled one is the PV at the top. As you can see, the different stages of the refrigeration cycle. You have your evaporation phase on the bottom, which is an isobaric process, which means pressure stays the same and your heat will be introduced into the system there. Then you have the compressor, which will increase the pressure of the fluid that you're working with. And then get to the condensation phase, where your heat will be actually leaving the system itself, and heading into the throttle phase, which decreases the pressure, once again, pushing it into the evaporator again. And that throttling phase is done through using the thermostatic expansion valve, which I'll get into how that works in a second. But there's different ways you can show the system. First though, ideal versus real. So from basic thermodynamic principles, you can find an ideal cycle which doesn't have any mechanical losses, any pressure losses, entropy, enthalpy losses in your system. But however, we know that that's not a real life scenario. So from this lab, we'll be getting a real cycle, which will be showing these real life scenarios, due to mechanical losses, having the valve in the system, having pumps that aren't 100% efficient, and things like that. And all the different types of devices we have aren't going to be 100% efficient. So you'll be coming out with a less, I guess, set in stone shape of your real cycle, which are shown there in the differences for the refrigeration cycle. So for some more background relevance, I guess, going over the entire system that we have primary functions will be the compression phase, the condensation phase, expansion phase, and the evaporation phase. For the evaporation phase, that's where your heat will be introduced from your surroundings and absorbed from there and put into the system. And your condenser will actually reject the heat back out from your system to the surrounding itself. And the COP is the ratio of your desired commodity, which will be either your heat in or heat out, over your magnitude of expenditure, which will be the work put into your system for the certain devices. So our apparatus, refrigerant 134 is the working fluid. We also have a water reservoir throughout. But as you can see here, we have your evaporator and your condenser. Picture here is the thermostatic expansion valve, which will control the flow rate, which I'll get into on the next slide, but controls the flow rate going into the evaporator so you can get the certain results that you want. You have your different pressure, temperature, and flow rate sensors spread throughout the areas, and then you have your controlled pump valves, or the computer controlled pumps there at the bottom. And the direction of flow of the fluids is shown with the arrows throughout the flow lines. So for the thermostatic expansion valve, pictured in between the condenser and the evaporator, it's trying to control the flow that is actually going into the evaporator. So if the temperature is too low in the evaporator itself, it's going to constrict that flow so it can heat up. If it has too much fluid going in to the evaporator, it's not able to heat it up as efficiently. So it's going to constrict the flow so it's able to heat it up and get a better output there, and vice versa in that sense. But there's an orifice plate, and that is the diaphragm can actually open or shut that valve based on what it's reading from the evaporator itself, where it's getting that reading from. So for test 1, the procedure, we're going to be comparing the inlet power of heat produced to find the COP. First, we're going to start the software, make sure that the evaporator and condenser are operable. Then we're going to set the flow rate, 5 liters per minute, switch on the compressor, set it to 40% of its capacity, and allow it to stabilize. And then we're going to record values for the power consumed, the temperatures at the inlet and exit, and the water inlet flow rate at the condenser. So finding the COP, as I said, it's the coefficient of your performance for the evaporator, which is the heat pump in this scenario. To find the heat rate into the water, use the equation here with the mass flow rate, and then your enthalpies for the temperature values at your system that you found. The power consumed, can also be found by the equation listed by W compressor, and that's over the efficiency of the system. And then with the ratio, you'll put either the heat brought into the system over the work done to get how actually your heat pump performed based on your expenditure of work put into the system. Test 2, making the pH diagram and comparing it to an ideal cycle. You want to start the system, making sure, once again, your condenser and your evaporator are working correctly. Set the compressor to 40% of its capacity. Run the evaporator side at a desired flow rate, 3 different flow rates pictured there. Allow the system to stabilize each time, and then you want to record certain pressures and temperatures at the inlet outlet of the compressor, as well as the condenser, and then at the expansion valve, and use these enthalpies found at these locations for pressure and temperature for the fluid, and then create a pressure enthalpy diagram and compare it to an ideal one. So in conclusion, COPs, like I said, measure the effectiveness of the system based on some background research that I did, and there being inefficiencies in real life scenarios. I predict a 75 to 90% efficiency based on heat losses and mechanical losses throughout the pumps, valves, and not having an ideal system, which would be 100% efficiency there. Also, we want to desire for this experiment to show the output will depend what type of system it is. For refrigeration, your heat will be heat loss in the system because you want to cool whatever environment that you're in. And then for the heat pump, you want heat gains, obviously in the system because you're trying to heat up whatever fluid that you have. In real life, analyzing COP can help with the system design, figuring out if you need to upsize or downsize certain devices in the system. And then lastly, the refrigeration cycle differs from the ideal due to pressure and different losses in real life. So, references and questions.